Hello, ladies and gentlemen. Today we're going to be talking about how to simplify radicals. And you may be thinking to yourself, well, didn't we already learn how to do that? We learned how to simplify radicals that are just square roots. So like in the past, we've learned how to simplify something like the square root of 49 is 7, or the square root of 32 breaks down into two square roots where 32 is divisible by 16 and 2, and 16 is a perfect square, which is 4 square roots of 2. So today we're going to be learning about how to break every kind of radical down, not just square roots, but cubed roots and fourth roots and even some fifth roots. So what you're going to need today is your notes or your tabbed notes, and then your calculator and your perfect roots table, that half sheet of paper that I gave you for your perfect roots table. That's going to come in super handy today. So in our tabbed foldable, we've already covered how to simplify exponents. And today we're going to be talking about, in this lesson or in this video, how to simplify radicals. So that's the flap that you want to open. So the inside should look like this, where you have 4 examples on top and 4 examples on bottom. Okay, so those are the examples we're going to go through today. Okay, so remember this perfect roots table that we've gotten in our notes already. So how we read that is that this would be my number, and then this is if I squared that number, and this would be if I cubed that number, this would be if I raised it to the fourth and to the fifth. So if we were to take, say, like the fifth root of something, that's going to lead us to the number that would be like the fifth root of 3,125 is 5. Okay, so we're going to use this table to help us reduce numbers and simplify radicals. Moving to the first 4 problems. We're going to try 4 problems without any variables or just numbers. So we're going to go through numbers 1 and 2. So number 1 is the square root of 40. This is something that we should be used to. We know that 40 is not a perfect square if we look at our perfect roots table. So that means that we're going to have to break up 40 into 2 square roots, where the first square root, or one of the square roots, has to be a perfect square that does go into 40. So if we look at our perfect squares list, the largest perfect square that goes into 40 would be 4, and 4 times 10 gets us back to 40. So we're splitting the square root of 40 into the square root of 4 times the square root of 10, where the square root of 4 we know is 2 square roots of 10. So we've been doing that throughout all the last 3 years of your mathematical careers. And so now when we move on to number 2, when we look for the cubed root of 40, we have to find, when we break it apart, we have to find a perfect cube and a non-perfect cube. So when we go to our perfect roots table and we look at our list, we have 1, 8, 27, 64. Well, I know 27 doesn't go into 40, and everything after that is larger than 40. So that means that my perfect cube that goes into 40 is 8. And then 8 times 5 gets me back to 40, so 5 is what goes in my other cubed root. So we know that the cubed root of 8, looking at our perfect roots table, is 2, and then what we have left over is the cubed root of 5. Okay, numbers 3 and 4. So if we have the cubed root of 72, we're going to have to split this up into the cubed root of some perfect cubed and the leftover factor. Okay, so if we look at our perfect cubed list again, we have 1, 8, 27, 64, and then 125. Well, 72 lies between 125 and 64, so I know it's not this guy. I know 72 divided by 64 isn't a nice whole number, and I know 72 divided by 27 also isn't a nice whole number, but 72 divided by 8 is 9, so 8 does it again for my perfect cubed. And so just like on our last problem, the cubed root of 8 is 2, and the cubed root of 9 we don't know. We know the square root of 9, but we don't know the cubed root of 9. So we can't simplify that any farther. I'm now moving on to the fourth root of 512. So we're going to be looking at fourth roots. So in your table, fourth roots, perfect fourth roots are 1, 16, 81, 256, and 625. Well, 512 falls between these two perfect fourths, so I know it can't be bigger than what my radicand is, so it can't be 625, and if I divide in my calculator, 512 divided by 256, I get an answer back that's 2, which means that my perfect fourth is 256 times 2. And if we look at our table, we know that the fourth root of 256 is 4, because 4 times 4 times 4 times 4 is 256. And then the fourth root of 2, we don't know, so that stays just like that. So that is how you would simplify radicals that aren't just square roots with just numbers. We break them up just like we normally do with square roots. Okay, moving on to the next 4 examples. Now we're going to be trying examples with not just numbers to break down, but also variables to break down. So example number 1, the fourth root of 625 x to the fourth. So I want you guys to split up for all these kinds of problems, to split it up into the fourth root of the number and the fourth root of the variable. So we can tackle them as like 2 separate problems within one. So let's first tackle the fourth root of 625. If we go to our perfect roots table, we see that 625 is a perfect fourth. It's in the column. And so we know that that fourth root of 625 is just 5. Now, we have the fourth root of x to the fourth. Well, if we rewrite this as a rational exponent, we know that the power is going to be my numerator and the index or the pocket is going to be my denominator. Well, x to the 4 divided by 4, well, 4 divided by 4 is just 1. So x to the fourth root of x to the fourth is just x to the first. So my final answer is 5x. Okay, looking at example number 2 now, let's split it up. So the cubed root or the third root of 64 and the third root of y to the 6th. So we split it up into the number and the variable. Well, if we go to our perfect table, our perfect roots table, we see that 64 is a perfect cube. So that means that this reduces to a whole number of 4. We didn't have to try to simplify it. It just simplifies nicely to the whole number 4. Okay, because 64 is a perfect cube. Now, if I change my y, the third root of y to the 6th, to a rational exponent, my numerator for my rational exponent is going to be 6, and my denominator is going to be 3. Well, 6 divided by 3 is 2, so that's 4y to the second. That is the final answer, but I also want to talk about another way that we can solve this one, okay? So if we have the cubed root of y to the 6th, we can think about this as how many groups of 3 make 6? Well, 2 groups of 3 make 6, and that's how I got my y squared, okay? We can also break this up. We can break up y to the 6th into multiple y's. We could do y times y times y times y times y, or we could also do y to the 3rd times y to the 3rd, and that's all getting to be the cubed root, which also breaks down into the cubed root of y to the 3rd times the cubed root of y to the 3rd, and those cancel, leaving us with y times y, which would just be y squared like we got. So there's lots of different ways that you can think about this. If you can change it to a rational exponent and get a whole number, that's great. But we're going to move on to number 3 and 4, and that sometimes doesn't happen. So we're going to have to rethink about how to go about those problems if it's not a nice whole number for our rational exponent. Okay, so for number 3, it's the fifth root of 4 times a to the 10th times b to the 6th. So I'm going to break it up into 3 radicals. I'm going to have the fifth root of 4 times the 5th root of a to the 10th times the 5th root of b to the 6th. Sorry, that's a b, of b to the 6th. Okay, so the 4th root of 5, well, there's no way we can figure that out. It's just going to stay like that. The 5th root of 4, okay, because 4 is too small. Now we have the 5th root of a to the 10th. Well, how many groups of 5 make 10? How many groups of 5 make 10? Well, 2 groups of 5 make 10. So that means I can make a come out of the radical and just say the exponent is 2. When we talk like that, or when we think like that, how many groups make the exponent? All we're doing in our head is basically a to the 10 divided by 5, which is a squared, okay? And now we have the 5th root of b to the 6th. Well, how many groups of 5 make 6? Well, there's only one group of 5 that goes into 6, and then we have this one left over. So we know that we can break this up into the 5th root of b to the 5th times we'll have 1b left over underneath the 5th root. But we know that one group of 5 goes into 6, so this just cancels to b, and then we still have that b to the 1st that can't go out of the radical because he's not in a group of 5, so he has to stay underneath. It's the 5th root of b. So it's kind of messy, and I'm sorry about that, but this is what we have left right here. We have the 5th root of 4 times a squared times b times the 5th root of b. So now we can actually do a little more combining and condensing again. So we're going to leave the stuff that's not underneath the radical out in front. So that'd be the a squared and the b. And now we're going to make a big radical with the 5th root. And what goes underneath is the 4 and the b. So my final answer, I'll circle in red, is a squared b times the 5th root of 4b. So that's my final answer for that guy. And I know that that's a little complicated, but that's how most of these are going to work, okay? So we got to think about it like that. Okay, now to number 4. I'll do this one in a different color. I'll do it in purple. Let's break it up so that we have the square root of 40 times the square root of x to the 5th. Okay? So if there's no, remember, if there's no index, we assume that it's a 2 because we assume it's a square root. So in number 1, actually, we broke up the square root of 40 into 2 times the square root of 10. Way back in number 1, we did this, okay? Now we have the square root of x to the 5th. So I'm just going to make a radical here to see what happens, but how many groups of 2 go into 5? Well, 2 groups of 2 go into 5, and we have 1 left over, okay? Or we can break this up into x squared, the second root of x squared times the second root of x squared times x, which becomes x squared times x to the 1st, okay? So again, there's lots of different ways that you can think about this, but the best way to think about it is to do how many groups of the index make the exponent, okay? And so however many groups that becomes, so like since 2 goes into 5 2 times, that means that I pull out an x squared, that 2 times, and then I leave whatever's underneath in the radical, okay? We're not done yet though, because we can combine this guy. We can pull the 2 and the x squared out in front, and then we can put the 10 and x underneath a common radical. So we have 2x squared outside of the radical, and we have the 10x underneath the radical. So that's my final answer for number 4. I know this is getting a little confusing, but I thought maybe if we watched this video before we came back into class and did some work together, we'd have some common knowledge, some common vocabulary, some prerequisite knowledge so that we can tackle more problems in class time when you get back from this video. So I want to thank you all for taking such good notes, and I shall see you soon.